Let's talk about consistency in Apache Cassandra. Now, this is the other half of replication consistency. So you need to have both of these working for you. Because when you replicate data, you need to know if it's there or not. And believe me, this is a hard topic in a distributed system. But Apache Cassandra has really got this nice combination of things that makes it work for you. And you are in control of how it works. So how does it work? So let's just take a quick review. The CAP theorem is something that describes a distributed system and the trade-offs. So consistency, availability, partition tolerance. Cassandra fits in that world of partition tolerance and availability. Now, partition tolerance means that you can do something like have nodes not seeing each other, the so-called split brain syndrome. And in that world, it is really hard to maintain your data. And most systems will just stop accepting data if you're in a partition event. And availability is what we pretty much want all the time when it comes to building large-scale applications. If you build an application that doesn't have high availability in mind now, you're probably going to get trounced by your competitor. So that's a good one to have as well. Consistency is the harder part in a distributed system. And Cassandra does not optimize for consistency. It gives you flexibility. You have tunable consistency. And you could tune away from availability or partition tolerance based on how much consistency you need in your data. But it is definitely optimized for availability and partition. So how do you tune consistency? Very important topic. Consistency levels are a part of the write. When you write data into the cluster, you have to tell it what kind of consistency level you want it to write to. When you read data, you have to ask for a certain consistency level. This is the control that you're given as a developer. When we write data in to the cluster, the coordinator is going to be looking at it, say, an RF3, 3 replicas, and understand that I have to write data to those 3 replicas. The coordinator is thinking those 3 replicas as destinations for your data. But how do you know if it got there or not? Well, we've specified in this case a consistency level of 1. These are a couple of terms you need to get familiar with. RF, CL. If you're talking to all the cool kids at a Cassandra conference, or you're talking about it in an architecture meeting, you start throwing out like, what's our RF and what's our CL? Super important. CL is really important when you're writing applications. In this case, a CL of 1 means that we only need one of the replicas to acknowledge the read or the write. So in this case, we get an acknowledgement from the first node, it's good to go. That doesn't mean that if we wrote data into the cluster that it doesn't write to those other replicas. It's just how fast it gets acknowledged. Now, CL of 1, because we only need one replica to acknowledge that write, you're going to get a lot more speed. So this is the fast consistency level. The data is still written to those other nodes. That is important to know. It's not that when you say CL of 1, I only want my data on one node. No, it's going to all the nodes. It's just how it gets acknowledged. So let's upgrade this. Let's go to quorum. That means that there's 51% of the nodes that acknowledge the write or agree on the result of the read. So in this example, when we write data in, I need 2 of the 3 nodes to acknowledge that that write has happened. If I don't get that, then I'm not satisfying quorum. Again, that doesn't mean that 3rd node doesn't get data. It's just not included in the response back to satisfy quorum. What if we can't stand any node down or any consistency violations, meaning that every bit of data has to land on a node and be acknowledged? This is where we go all the way up to CL of all, meaning that every replica has to acknowledge the write or have a consistent read. And this is not one that I really recommend, because what you're doing essentially is you're turning off any of the partition tolerance or availability and going all the way to consistency. Now, it may be that you have a use case for that, but just think about what you're doing here is that you're creating a situation where those 3 nodes are pretty much one big node. And everything that happens in your cluster will be totally tied up in the fact that you have everything at CL all. Quorum is a really good place to be. It's the middle ground. 51% is pretty good. On read and on write, you're going to get consistent data. It's known as strongly consistent. When we write data at CL of all, that means that all that data has to be acknowledged by every single node and go back to the client saying, I got it, it's good, it's on every single node. Not only is it going to be consistent though, it's going to be slow. If you have a consistency level of all in 3 nodes, you have to wait for 3 nodes to reply. That could take a while. So how do we get strong consistency in a large-scale distributed system? Strong consistency means I'm reading the data that I just wrote into the cluster. Really important. You don't want to get stale data. So if I'm writing data into the cluster and I need strong consistency, writing it as a CL of all means that I have acknowledged the write on every single replica. Great, we know that the data is there. And when I need to read the data, the consistency level now at all at write gives us a little looser consistency requirements on the read. In this case, we're going to read at 1. Since we know the data got there at consistency level all, reading at 1 means that any one of those replicas is going to be just fine. It'll have the data we need. It's not going to be stale. So this is an example of strong consistency. The data I wrote in is the data I read out. Awesome. Now in the example of using all to write and a 1 to read, probably not the best production way to do things. Again, consistency level of all is really restrictive. You can't have an outage. It will shut you down. So how can you do this in a way that's a lot more flexible with regards to availability, which we're going to try to optimize for? Looking at this example, same cluster, when we write data in, we're going to write it in at quorum, meaning that 51% of the nodes acknowledge the write. But in the read case, we're also going to read at quorum, meaning that we're going to have to get a consistent read back. This is how you maintain strong consistency without sacrificing availability, which don't do that. We do that too many times with our systems where we make really terrible sacrifices. You don't need to do this in an Apache Cassandra cluster. Because of the way it works with the 51% read off of 51% write, you will get strong consistency. You will read the data that you wrote into the cluster. And this is really important to understand when you need strong consistency in a production environment. And this is what you need in your application to keep it online and your data consistent, which is kind of the name of the game, right? Now, what about a CL of 1? When is that ever useful? Well, surprisingly enough, it's very useful because you can't say that every bit of data that you ever read or write is going to need to be strongly consistent. Think about log data, time series data, IoT. Eventually consistent, meaning a few milliseconds here or there, not really a huge requirement. But in this case, we need really strong availability, meaning that it's always online, and most importantly, we need the speed. We don't need to burden the system with trying to manage quorum or alls or anything like that. The client just needs to write data and move on. In this example, when we're writing data into the cluster, when the client writes, it says, I want a consistency level of 1. That consistency level of 1 just means that one node acknowledges the write, and when I do a read, I want one node to acknowledge the read. That's it. That doesn't mean that we have random data sitting on all these nodes. Now, remember, when we write at 1, all of those nodes get consistent data. They're just not asking for the consistency. So when I read my data, I'm just saying I'm okay if the data is a little late. In the case of like an IoT or something like that, that may not be a problem. Now keep in mind that in a running cluster that's healthy, you're looking at very low latency numbers, maybe a millisecond or a microsecond between those. So it's not that big of a deal. It's not like next week it'll be available. But just know what you get. When you write at 1 and read at 1, that's the expectation. So how about across data centers? That's the tough one. And there's some really specific consistency levels that are specifically for multi-data center. Remember, Cassandra was built on the idea of replicating data not only locally, but across everything. Around the world, across the country, wherever you need your data. Strong replication with consistency. That's the name of the game here. But in multiple data centers, let's look at how that works. So in the case where we write, we know that whenever we replicate the data, we write it to the coordinator. The coordinator's job is not only to write to the local data center, but also to write to the other data center. But if I do this and I want to make sure that I'm getting consistent data in the first data center, and I use, say, quorum, quorum is going to be a little heavy because that means that it's going to be looking at all the nodes across both data centers, which means that I have to wait for the response, maybe from west to east, United States, that's 70 milliseconds of latency. That's not going to work for me. I don't want to wait 70 extra milliseconds for a quorum. So there's this idea of local quorum. Local quorum means that whenever I write my data into the data center, or I read my data, that it's only looking at consistency in those nodes, the replicas inside that data center. The other data center is not considered in a local quorum. And that doesn't mean that it won't write to that other data center. It's just not in the calculation for the quorum. And that was really how you keep your data model working in multiple data centers without sacrificing a lot of speed when you need that stronger consistency. So how many different consistency levels are there? Well, that's kind of funny part of Cassandra. There are a lot of them, and most of them, quite frankly, are kind of useless. But they've been added over the years in the project so that they have different use cases that they are applicable. Some of these aren't as useful and some of them got superseded by others, but let's look at this table. So all the consistency levels are listed here. And if you look at this table, they go from the weakest to the strongest. Now let's start at the very top. The consistency level of any. Let me just caution you, the only reason it's listed here is because it exists. And I don't want you walking through your life, running into any and thinking this is amazing. It's not. It was put in there for a very interesting reason that never really worked and has never been taken out. So any is not something you really want to use. It means that you have no replicas available. You're throwing data into your cluster and hoping for the best. I don't think that's a good idea. So just ignore it for now. It exists. Moving on. The one you should start at the very lowest level is 1. And there's 2 and 3. 2 and 3 are also ones that I don't ever see in production. 1 is the consistency level that you see a lot, along with quorum. So those two are really the meat and potatoes of what we built here. But there are other ones that you can consider. For instance, we have the local versions. Local means that there's consideration with other data centers. So some of these operations occur only in one data center, so they don't multiply the effect across multiple data centers. Each quorum is kind of an exotic version of quorum, meaning that each particular data center has its own version of quorum, so there's 51% in each data center. Again, very heavy, rarely used, just know why it exists. And then finally, all, the most consistency you can get, ever. Now with all, you have absolutely no chance of maintaining uptime if you have a node failure. This is it. It's very strict. You're saying I'm all in on consistency and I'm not in on availability. Not where you want to be, probably. So use that wisely, but most likely you're just going to use 1 and quorum or local quorum if you're in a multi-data center situation. And those are the ones you'll stick to mostly for your strong consistency or when your consistency needs are a little less. So just to wrap this up, remember consistency is such an important part of the replication story. They glue together. I've said this so many times in the past. If you want to understand how Cassandra works, you have to understand replication and consistency. Replicating your data around like a cowboy, that's great, but you are a developer who needs to understand where your data is, and that's where consistency level comes in. You get to know where your data is. Awesome. So just think about the trade-offs. And that's really how you pick your consistency level. If I need low latency and I'm not so concerned about stale data, 1. If I have a lot more concern about consistency and maybe even uptime for my data, quorum. But both of these things are things that are trade-offs, and you can make a good decision now that you know how they work. So let's try an exercise with consistency level and see how they work in practice.